So one of my favorite childhood hobbies was photographing electromagnetic radio waves and photographing sound waves. And so what I would do is I'd have let's say there's a transmitter, an antenna it could be, or it might be a speaker or a trumpet or a sound source. Maybe there's some kind of sound source here. And then we take a little bit of that sound source, whether it be from the sound source itself, or we can put another little microphone here and feed that into a lock-in amplifier, the reference input of a lock-in amplifier. And then we have another microphone right here physically attached to a display device of some sort. It may be a screen, an oscilloscope screen, or a computer screen, or a row of LEDs or something attached to that. And that microphone goes into the signal input, and then the output of the lock-in amplifier goes to this display. And this display and the microphone move together, and it allows us to photograph the sound waves coming from this sound source. Alternatively, we can attach a speaker to the display and have a microphone here, and then I call that meta sensing, the sensing of sensing, sensing the microphone's capacity to sense. So what the lock-in amplifier does is, in a sense, it just takes these two inputs, the reference and the signal input, and multiplies them together, and then low-pass filters the result and outputs that. So let's say that we have our sound source here. It's a cosine wave, let's say cos omega t, and it propagates. The sound propagates outwards and is moving at the speed of sound. So this wave here is something of the form cos omega t minus kx. So this is a moving wave. What that means is that that wave is a function of both time and space. So it's moving, and say this is the x direction here, the x coordinate, and I'm only going to consider it in one dimension for the time being. So it's a function of time and space, and this is a space-time continuum. And so that wave is moving in space-time. And what we're essentially doing is taking the wave that we receive, so we're going to pick up this wave by some microphone or whatever, and feed it into a multiplier, and then we're going to take some of the wave that we sent out, either by a reference near the transmitter. If this is a trumpet or something, we'll have a microphone right beside it, and that microphone will go in here. Or if this is a speaker, we could just take a little bit of the signal generator that's being fed to that speaker and bring it in here. And so now, then what we have here is when we take a low-pass filter of this, and then out comes this signal. Before the low-pass filter, what we have is cos omega t times cos omega t minus kx. And by a simple trigonometric identity, that is equal to, and by a simple trigonometric identity, this is equal to 1/2 cosine of the sum omega t plus omega t minus kx plus cos omega t minus omega t minus kx, which is equal to 1/2 cos 2 omega t minus kx plus 1/2 cos kx. Cosine, symmetrical, so cos of negative kx is equal to cos of positive kx. And what this low-pass filter here does over here, so that's what we have here, and then coming out of here we only have this lower frequency term, because you see this 2 omega t, that's the carrier frequency, twice the carrier frequency minus a little bit of kx, plus 1/2 cos kx. If you look at the spectrum of what's in here, If you have a carrier frequency, like let's say we're doing a sonar and we make it at 10,000 hertz or 20,000 hertz, 40,000 hertz, whatever it is for sonar. Say it's a 40 kilohertz sonar, we're going to have coming back here 80 kilohertz here, plus, and the little bit of difference, the little bit of Doppler shift, which is much smaller. And so we're going to have that Doppler shift is the only part that's going to come through the low pass filter, and that's going to be near the baseband. This is relatively low frequency. So the speed of sound, for example, the speed that you're moving compared to the speed of sound is going to be in this ratio. So, or if it's for radio waves, the speed that you're moving compared to the speed of light is going to be in the ratio similar to the frequency of the radio wave versus the frequency that this is. So this will be at a much lower frequency. So the low pass filter will just filter out this part here, and we'll just be left with this half cos kx. So what we're going to have here is half cos kx. And that's a function only of space and not of time. And so you can see it takes time out of this. So this gives rise, when we do this, when we have this apparatus in which there's a slowly moving device. So if I've got my speaker here and it's emitting sound waves like this, and then I have over here some kind of a display device, and it has some kind of a, say, a microphone on there attached to it, and it moves with it. It will display this waveform as a function of space. So it's as if the wave is sitting still. I call that a sitting wave. It's as if we're traveling at the speed of sound and matching the speed of sound of that wave, and we can see that wave totally sitting still. And so what you see, if you take a long exposure photograph, for example, of this display moving and the dot simply moving up and down, if you just display a dot and the dot moves up and down in proportion to the number, the numerical value of this, 1/2 cos kx, it will display that waveform, simply that cosine wave. And typically, of course, it'll get stronger when you're closer to the speaker and weaker when you're further away, so it'll look something like this. If this is the speaker right here, and we're taking a photograph of the sound wave it produces, you'll have this cos wave that's fairly strong near it, and it'll just get weaker as you get further away from it. And of course you can see this wavelength. This is the distance. This is the wavelength that you'll be able to actually see and photograph, this wavelength of sound. So for example, if the speaker is transmitting a sound wave at 440 cycles per second, then, and we know the speed of sound is about 334 meters per second, 334 meters per second divided by 440 hertz, which is just per second. The per seconds cancel, and that's about 3/4 of a meter. So that's about 30 inches or so. So we'll see about 30 inches between every cycle of this wave, if this is an A440. So we can photograph that A440 sound wave. And of course, if this wave is some other shape of a wave, more generally, we can photograph a differently shaped wave. Maybe it's a square wave, and it'll get a little bit weaker as it gets further from the source. So this may have harmonics in it, and we can actually photograph those harmonics. So more generally, this reference signal may have harmonics in it. In fact, that reference signal can have a spectrum that just has all frequency components in it. And when you multiply this reference signal by the waveform that we receive from here, we'll reconstruct and be able to see and photograph the sitting wave as if we were traveling at the speed of sound right next to it. Now let me introduce just a slight variation of that theme. Suppose we have a signal generator that can generate both a cosine wave and a sine wave. And we take the cosine wave, take either of them, it doesn't really matter. Let's say we take the cosine wave and we feed that into a speaker, a sound source such as a loudspeaker, which then emits these sound waves. And now we take a microphone here that's picking up the sound wave, and we do what we did before. We take that cosine wave that we sent out and we multiply it by whatever that signal we receive is, but we also take the sine wave that we sent out and we multiply it by the same signal here, and then we run each of these through a low pass filter. And then we drive that result into the X and Y inputs of a display screen such as an oscilloscope, an XY plotter. And this cosine wave goes into the x-axis and the sine wave goes into the y-axis. What we'll have now is, instead of plotting out just a wave going up and down, we're going to now see on this screen that it'll go around in a circle. And when we bring the speaker and microphone closer together, the circle will go counterclockwise, positive frequencies. And when we bring the speaker and microphone apart, the circle will go clockwise. So then when we photograph that sound wave, if we attach this microphone to the moving oscilloscope and we move it back and forth, instead of having it face us, face the camera, we're going to turn it sideways so it's facing this way, and we're going to photograph it from over here so we can see it kind of three-dimensionally. And as it moves here, what it'll do is it'll trace out this spiral pattern. It's going to go around like this while it's moving, so it'll trace out this shape that looks like a helix or a spiral, which of course is stronger closer to the speaker and weaker as I get further away. So that you draw kind of like this as it moves across. And finally, if I have some sort of sound source, say it's a trumpet or something, a musical instrument that's making sound at multiple harmonics, sound waves are coming out here at not just one pure tone but multiple harmonics, I'll put a microphone here, which is my reference microphone. I'll run that into a phase lock loop, PLL, from which I will generate a cosine wave at the fundamental frequency and a sine wave, and I'll generate all of the harmonics as well. So this will become the reference generator, and then so there's going to be a sine wave at the fundamental at twice that frequency, 4 times that frequency, and so on, likewise with the sine waves. So the cosine part, its spectrum is just going to be a Dirac comb that has everything in it, all the harmonics. This is the frequency. And so what's going to happen now is I'm going to multiply these reference signals. I'll call that the ref rater, and then there is a moving microphone here, and that's going to go to both of these. And then there's a low pass filter here, low pass filter here on each of these. And then this is going to my XY plotter scope. This one goes into the X input and that one goes into the Y input. And then this scope will trace out the pattern with all of its harmonics. So this is a special kind of lock-in amplifier in a sense that lets through all the harmonics of the signal. A special type of lock-in amplifier, specifically designed for photographing or visualizing sound waves or radio waves. And what it does is it lets through all the harmonics and allows us to see, as this pattern evolves, all the harmonics of the signal in three-dimensional space as it moves through the space. So this allows us, in a sense, to photograph these different waves. There's waves. Waves are all around us everywhere. Water waves, radio waves, sound waves, 5G, everything. So now all of a sudden we've got a system that allows us to capture and photograph and document and see these waves. So, you know, if I have a wave like this and real and imaginary parts of it, it's easy to see that. But now the wave can also have various components. You know, it might have different frequency components in it. So I might have, you know, where the real part is a square wave, and say that's the real part. And the question is, the fundamental interesting question is, what should the imaginary part be when I'm actually visualizing that wave? Should it be the Hilbert transform of a square wave, or should it be a square wave that's shifted? You know, the same wave shape that's shifted by 90 degrees, which is not the Hilbert transform of a square wave. So this is kind of a fundamental interesting question to ask. What should we be seeing when we take a complex valued wave and visualize X versus Y? That's a really interesting philosophical question to try to answer. Do a little bit of beach cleanup here too. A little bit of beach cleanup.